Hello everyone. In this video, we will learn about a new notion called conditional probability. We'll start with an example and then develop the theory based on this example. This is a simple example. If hair dye is rolled twice, what is the probability that sum of the numbers that come up is equal to 10? Well, remember that to work with experiment rolling a dice twice, or rolling two dice, we need to consider this an equiprobable sample space. The best one is this one. So you basically list all the outcomes. Then we'll go up to 2, 6, and this will go up to 6, 1, up to 6, 6. And this includes all possible outcomes there, and you know that n of s is 36. And the event that we are going to study is the sum of the two numbers that come up is equal to 10. So here, well, the smallest number that come up and give us the sum equal to 10 is 4 and 6, and then you go 5 and 5, and then 6 and 4. These are only three possibilities that the sum is equal to 10. So n of e for that sample space is going to be 3. Well, then if you're looking for probability, we know that for the equiprobable sample spaces, this is basically NE divided by NS, which is 3 over 36, 1 over 12. It's a simple case, yes? But now we are changing question a little bit. If hair dye is rolled twice, as before, and it is known, well, someone saw it or someone recorded that, the first time, the first roll, an even number come up. This is known. And now we are looking for probability of the sum being equal to 10. So basically we are looking for probability of E, knowing that first roll gave us an even. So how should we deal with this case? Well, one thing here to note is that the old sample space, well, just based on the information we have, won't work here. For example, we won't have any 1-1 case, because in 1-1, the first entry is not even. Well, maybe I should go ahead and define another sample space. Okay, I'm saying sample space, I'll go back to S again, but let's just see it this way. So my sample space this time will only include the cases that has the first number even. So I will have 2, 1 to 2, 6, and 4, 1 to 4, 6, and 6, 1 up to 6, 6. Yes. And you see that n of f, so this is the place that everything happening, and you see that this is now equiprobable space because all the points are equal. If you look at the previous one S, the probability that 1-1 is, knowing that we have the first one even, is not anymore 1 over 36, it's 0. We already know that 1-1 is not there at all. So NF here is 18. Okay, how is this going to help us? Well, we are looking for probability of E, knowing that we are working with F here, and well, that will give us, okay, what are the possibilities of E for which the first number is even? Well, here is going to be 4, well, remember E was this, yes, but 4, 6, and 6, 4 are two acceptable cases. 5, 5 doesn't work anymore because we know that first number was even. 5 is not, does not have even first number. And then divided by the whole possible numbers that your equiprobable sample space has. Well, I will write just NF, and you see that this is 2 over 18, and that is 1 over 9. Yes. And you notice right away that, oh, knowing some information or having some information about what happened we may change the probability. And just knowing some extra piece of information would change our probability to so-called conditional probability. But the way I wrote everything here, it's just like you may say, okay, each time I have to go define a new sample space and so on. But to be honest, you don't need to do that. First thing here is that you see I can divide both numerator and both denominator by n of s. And doing that, you see that the denominator is going to be probability of f, considering the sample space that we had before. And in the numerator, you say that, oh, there is no e here, there is no f, but if you look carefully, we basically found the intersection of e and f, things that are in e and are in f. So basically what we had here was e intersect f in the numerator, count the number there, n of s down there. So what we found basically was probability of intersection of that divided by probability of the given part. And doing that, you see that not only we are considering seeing a new case, and by the way, that is what we have conditional probability. We also see that there is, we kind of cooked up a formula, and that formula will work in general. So let me just write this one, probability. Okay. So what is that? So let's assume that, E and F are two events from the same sample space. Then the conditional probability of E given F or knowing F, this is, we denoted by this. We are looking for probability of E knowing that F happened or given that F happened. There's a line there. Okay. Is the probability that E happens knowing with the knowledge that F already or for sure happened. So we know that the first entry is even. Then let's find probability of the event that sums of two numbers are 10. So probability of E knowing F. And the formula for the conditional probability, as we had above, formula for conditional probability is given by this. So you're looking for probability of E given F. This is going to be probability of E intersect F in the numerator divided by probability of F, or the given part, in the denominator. Well, here you know that we are assuming the probability of F is not 0. We cannot divide it by 0. If it is 0, this conditional probability is going to be, at least for our case, is going to be 0. So that is the conditional probability. That is the formula. Let's do some example and see how this works. A single card has drawn from a starter deck, and it is known that the card is a number. So here something is known. So let me write it as F. The card is a number. Now we are looking for probability of the card is red. So what is the card is red? And what we are looking for is that with the knowledge, or knowing that, given that the card is a number, what is the probability that the card is an even number? Okay, sorry, it's a red card. So this means that we have to find probability of E intersect F divided by probability of just F itself. But probability of F, having a number card, there are 36 number cards and there are in total 52, but the number cards that are red, only half of them are red, because there are diamonds 2 to 9 diamonds, 2 to 9 heart, so there are just 18 of them which are red and number, and divided by 52. And then you see that this cancels with that, and that is equal to 18 over 36, which is 1 over 2. Let's do another example. Let E and F be two events from the same sample space. What is probability of E knowing F? Well, the formula says that we have to find probability of the intersection, then divided it by probability of F. Probability of F is given, it is 0.45. How about the intersection? When I come see that, okay, probability of E is there, probability of F is there, probability of union is there, what inclusion-exclusion principle will give us the probability of intersection? It says that add probability of E to probability of F, subtract probability of the union. And that is 0.3 plus 0.45 minus 0.7, which will give us 0.05. And that is where this guy comes from. And I can put 0.05, and that is just 5 over 45, which is 1 over 9. And that's conditional probability. So in other videos, we will do more examples. For now, you just need to know the notation, and you just need to know the formula and be able to translate the scenarios that similar to what we had into conditional probabilities.